Diffraction, interference, and double slit experiment. When sound waves and water waves meet an obstacle, they bend around it. This bending is called diffraction and explains why you can hear a person around a corner even when you can't see her. Sound waves bend or diffract. When waves meet a small opening, the opening generates a new wave on the other side. The picture shows a wave moving from right to left. Right here, the waves are pretty straight. They've been going on for a while. They have this little opening here, and look, the wave regenerates, so you start getting these curves. And then farther out, the waves would look straight again as the circle gets bigger. So what's going on here? Let's say this was sound. If you were here, you could obviously hear the sound coming through. But guess what? Even when you're over here, see how the wave spreads out? So you can still hear the sound on that side. So that's diffraction.
It was also observed that light bends around certain objects, and when it meets the light from the other side, it would create a bright spot where it would be least expected. For example, light that is shown on a coin would create a shadow behind the coin. Of course, that's what we would expect. But in certain cases, depending on the light wavelength and the coin size, you would see a bright spot right over here, right in the middle of the shadow. In this case, what's happening is the bent light, or the diffracted light, from one part of the disk would interfere with the diffracted light from the other part and produce a bright spot in the middle. Let's put these two observations together. What if we have two or more wave sources bending around an obstacle and then running into each other? Well, you would get a picture like this that we have here on the left with water waves. You have different patterns of water waves coming from different points, interfering with each other and creating this different pattern of waves. These two phenomena of diffraction, where a wave bends around an obstacle, and interference, when the waves, after they bend, will combine with each other and make interesting ripples, for example, or patterns. Thomas Young, in 1801, decided to see if this would work with light, and we call this the double slit experiment. In the case of water waves, the interference effect becomes more pronounced as the wavelength of the water wave is closer to the width of the opening. So if we want to see this in light, we need much smaller openings or gaps for the light to pass through, since light's wavelength is much smaller than water waves. But first, let's see if we can explain this using Newton's optics. We're going to assume light is a particle, and we're going to predict what would happen if a beam of light particles was incident on a wall with two holes in it, and we'll use a baseball pitcher analogy. Here's where we use the baseball analogy. We take light as a particle or a baseball, and let's say we clone one of the most historical pitchers of all time, Cy Young, and we have one Cy over here, another over here. And he's going to be throwing baseballs that are a little smaller than this little hole in the wall. You would obviously expect that any baseballs thrown here would collect over here in the red spot, and any baseballs thrown here would collect in the blue spot. So if light was considered merely as a particle, or a great number of particles, you'd expect to see a similar pattern. But instead of baseball collection baskets, you'd have photoelectric detectors, which would count the number of light particles hitting it. But when Thomas Young set up his experiment with a single color of light, or monochromatic light, he did not see two bright patterns. For example, if they were baseballs, you would expect to see a large amount of light collected over here and also here, in line with these two slits. But what he actually saw was an interference pattern, where there would be alternate bright and dark patches of light, which decreased slowly in intensity from the peak brightness right here in the middle. This is where the light was brightest, not even in line with these double slits. So the physical experiment did not back up the prediction. Here's the actual sketch that Young made with his results. We have the 2-point sources over here where the light was allowed to pass through. Notice how he drew the waves here, just like we had with the water waves earlier, right? When light hits here, or a wave, it then regenerates a new outgoing spherical wave, and you can see how these are going to combine and interfere with each other. And he labeled a couple points here to show the specific effects. And if you kind of look at this, you see dark spots there, then kind of a bright spot over there. So you get that alternating bright-dark pattern. The key point that explains why interference occurs is the distance that the two sources of light travel to get to the observation screen over here. These two waves here, frankly, travel the same distance to get over here. If I take a point down here, this wave travels a much longer distance than this does. In this case, a similar effect. And the point is, depending on the path length difference, the wave can either interfere constructively. For example, if the waves meet each other something like this, at the same point, they add, these two maxima add, and you get a larger value. But if they were to come somewhat out of phase, for example, like this, you have a maximum here, a minimum here, they add up to 0. And in that case, that would be over here. That would give you a dark spot, which would be destructive interference. And over here, where the light waves arrive in phase, you would get a bright spot, and we call that constructive interference. This was shown earlier in the waves chapter. Waves will constructively interfere if they reach a point where they are both at a maximum amplitude. This will occur when the distance they travel differs by an integral number of wavelengths, like 1, 2, 3, 4, etc. The constructive interference will give you a bright spot, or it's typically called a fringe of light. Dark fringes will occur between the bright fringes.
This is a photo of the monochromatic light, comes from over here, goes here through the double slit, striking a distant screen after passing through the two slits. It is the same pattern that results from sound or water waves. Hence, Thomas Young made the conclusion that light, like sound and water, traveled as a wave.
Using a little algebra and geometry, the position of these bright fringes is determined, and it is this equation here. X sub m equals m lambda L divided by d. And m is 0, plus or minus 1, plus or minus 2, etc. This tells you what order the fringe is. As you remember from the picture shown earlier, there are multiple fringes. There's a very large bright fringe here in the middle, and then there are more fringes as you go up, more fringes as you go down. The positive values of m refer to the fringes going in the up direction. Lambda is the wavelength of the light. L is the distance between the two screens, the one screen with the two slits, the two openings, and the other screen with the detection devices. D is the distance between the slits. The experimental results, as explained by the equation on the previous slide, will give us a brightness versus distance plot. Right here in the middle, this is the central maximum, and you can see how its intensity, its brightness, is greatest right here. Then evenly, very evenly, the intensity falls off, and you can see the maxima occur at specific distances here. They're all the same. And we have, again, this decreasing intensity as we get further away from the middle of the experiment. To summarize, the double slit experiment relies on two properties of waves, diffraction and interference. These enabled Young to claim that light is a wave. You start here with a monochromatic light source. The light passes through the two slits here, and each one generates a new wave due to diffraction. These waves then either constructively or destructively interfere, there's the other property, on a screen over here, and remember the distance between these two screens is L, where this distance L is much greater than the distance between the two slits.
In a Young's double slit experiment, the slit separation is 0.2 millimeters and the distance to the detection screen is 1.8 meters. Light of wavelength 640 nanometers is incident on the two slits. How far from the midpoint of the detection screen is the first maximum? The givens are right up here, and a lot of unit conversion had to go on, right? We had nanometers here, had to convert that into meters, and 1 nanometer is 10 to the minus 9th meters. L was okay, that was in meters. The distance between the two slits, millimeters, 1 millimeter is 10 to the minus 3 meters. So everybody has to be in meters so it works out. Here's our double slit equation, and we're looking for the first maximum, so that means m is equal to 1. We now substitute in our givens, and here's another reminder, make sure all distances are in meters. And we put our numbers in, and we come up with 0.00576 meters, which is absolutely correct, and you would get full credit. But here, we've converted it over to millimeters by moving the decimal 3 places to the right, because in the lab, the distance from the midpoint of the detection screen is commonly measured in millimeters or centimeters, certainly not meters. In a Young's double slit experiment, the slit separation is 0.34 millimeters and the distance through the detection screen is 2.8 meters. The fourth maximum is found at 2 centimeters. What is the wavelength of the light? We list the givens, and m is equal to 4 because we're looking for the fourth maximum, and we convert all distances to meters. Okay. 1 millimeter is 10 to the minus 3 meter, and 1 centimeter is 0.02 meters. Here's a double slit equation. We need to solve for lambda, so we'll multiply both sides by d and divide both sides by ml. And that will get rid of everybody over here, which is nice, and you'll just have lambda, and then you have x times d over ml, which is what we have here. Now substitute in the givens, and you'll get your answer here, which is perfectly acceptable. But typically in the lab, when you're dealing with visible light, you use nanometers. So if you have 10 to the minus 7 meters, you do a little unit conversion here, where 1 meter is 10 to the 9th nanometers. So these cancel, and you'll be left with nanometers, and here it is, 607 nanometers.